Okay, so today's topic in Math 31 is going to be rates of change with triangles. It's going to be very similar to the related rates concepts that we covered with volume and surface area in the last couple days here. It's just going to focus in on triangles today rather than actually three-dimensional shapes. So this is the last topic of Unit C. That was the applications of derivatives unit, of course. It's going to seem, like I just said, similar to the rates of change of area and volume questions we did a few days ago. Implicit differentiation is going to become super key again. There's a bunch of different formulas with triangles that we'll have to remember, though. I think some of them are on your formula sheet. You'll have to double check. There are extra digital copies of the formula sheet on Google Classroom. So if you've misplaced yours or if you don't have one at home, you can always check it there. I'll have to get back to you as to whether or not it's on there. I don't have one in front of me, but don't worry, I'll provide them for this lesson today. Before we get rolling here, just because you don't have a printed notes package or anything for this, or if you're just wandering in and watching this video some other time, just try to pause the video when you can and take some notes on this one. Some of the questions are a little bit wordy, but it would be worth it to just have it down in your notes somewhere. But again, you're your own learner. If you think you don't need to do that, then that's fine. At least follow along and understand how we approach these kind of problems. Anyway, first of all, before we begin, let's just remind ourselves some of the rules that surround triangles here. Triangles can, of course, at least so far in math, be divided into two broad categories. We have right triangles, which use these formulas, and non-right triangles, which was the whole big chunk of Math 20 that we dealt with, which use those couple formulas right there, right? So again, for right triangles, we have Pythagoras' theorem that goes way back to like grade 7 or 8 or whatever. Then we have all these guys, just your normal sine, cos, tan, SOH, TOA, as we would remember, right? Opposite over hypotenuse for sine, adjacent over hypotenuse for cosine, opposite over adjacent for tan. So those are the more basic ones for right triangles. So if you have a right triangle, you get to use those. They're a little simpler, right? For non-right triangles, we had a couple of like somewhat more complicated formulas to use here. We had sine law, which said that sine of an angle divided by the side across from that angle, hence the uppercase and lowercase letters, equals sine of another angle divided by the side length across from that angle, which equals sine of another angle, excuse me, divided by the side length of the angle across from it, right? So in other words, all of these relationships within a triangle are always the same. Sine of its angle divided by the side length across from it is the same as sine of any other angle divided by its side length across from it. Now I know I put in here SSA or ASA triangles. That means if you know two sides and an angle that was in between them, you can use sine law. Or if you know two angles on one side, you can use sine law as well. The easiest way to remember sine law for me is you need to look for an opposite pair. So if you know set in stone an angle and the side length across from it, then you're golden. But it has to be set in stone. And you're going to notice with these questions here today, oftentimes the certain side lengths will change. So if it says something about a constant side length, maybe sine law can be used. Cosine law was like basically your last resort. It is a lot more cumbersome to use. It said a squared equals b squared plus c squared minus 2bc times cos a. There's a lot to break down here. Basically, the main idea is side A right here and angle A right here. They have to be opposite to each other. So it's not that you know these pairs. One of them could be an unknown and you have to solve for it. But that is just the relationship that occurs. And this is usually used in SSS triangles. So triangles where you know all three sides and you don't even know a single angle. So you can find angle A right here. Or SAS triangles where you know two sides and the angle that is located right in between them. So we're going to need to use these relations to determine how related rates between numerous variables can be connected. You're going to find out with triangles here, as opposed to three-dimensional shapes, there's a lot more variables to keep track of. So follow along as we go over this first question here. So this is a classic kind of question. It's a ladder leaning up against a building. We've got a 15-foot long ladder leaning against a building, and the base of the ladder starts sliding away from the wall at a rate of 2.5 feet per second. Now, at what rate to the nearest hundredth is the ladder sliding down the wall at the point when the top of the ladder is 3 feet from the floor? Okay, so there's going to be a bit of a weird roundabout way of doing this. I always like starting by drawing a picture, right? It doesn't have to be super elaborate, but if we get a picture drawn here, let's say this is our building. Let's say this is our ladder leaning against the building. We know the ladder is 15 feet long, so we'll put 15 right here. Now these side lengths are going to change because this ladder is sliding away from the wall at a rate of 2.5 feet per second. I was just double checking that I was reading that correctly. Yes, the base of the ladder. The base of the ladder is sliding away from the wall at a rate of 2.5 feet per second. So logically, if you just think about this, if the base of the ladder is sliding away from the wall, this side right here, this x coordinate, we could say, is getting bigger. Whereas our vertical height of our ladder, we'll call it the y coordinate, is going to be getting smaller because it's going to be going down the wall here. So let's kind of take inventory of all of the little pieces of information that we have. We know 15. That's set in stone. That's not going to change. This ladder is not going to extend or shrink or whatever. That's no big deal. The next number we know is 2.5 feet per second. And that is the rate at which the base of the ladder is sliding away from the wall. You could say that that is the rate of change of our x value. Our x value is getting bigger at a rate of 2.5 feet per second. If it's a rate of change of x, why don't we just call that x prime? That is the derivative of x with respect to time. After every second, it's getting 2.5 feet bigger, right? So we'll say x prime equals 2.5. There's one number down. All right. Next thing it says, at what rate to the nearest hundredth is the ladder sliding down the wall at the point when the top of the ladder is 3 feet from the wall? Okay, so what we're looking for here is the rate at which the ladder is sliding down the wall. So we're looking at the rate at which it's going down this way. If this was the rate at which it was going away from the wall, then y prime would be the rate at which it's going down the wall. So I'll say y prime equals question mark. That's what we're looking for. Other numbers we have here, it says at the point when the top of the ladder is 3 feet from the floor. So the top of the ladder is 3 feet from the floor. That sounds like that would be our y value. So we'll say y is equal to 3 feet. And that's all we have for numbers right now. So unfortunately, what that means is we now have to think about what kind of relation exists in this situation. Now, the good news is it wouldn't be too far of a stretch. I guess I really should have put it in the question, but it's not too far of a stretch to suggest that this is a right triangle. If it's leaning up against a building, buildings typically are built, of course, at a right angle to the ground, right? So in other words, that's not a big stretch. Maybe I should have put it in the question, whoop-de-doo. Since it's a right triangle, we know we can either use Pythagoras or our SOHCAHTOA stuff to tackle this kind of a question. Now, I wouldn't worry about SOHCAHTOA because this question never mentioned at any point anything to do with an angle, right? Didn't tell us what the angles are here. I'm sure you could find it, especially if you knew y was 3, but we don't care about that here. So what we do care about, because we care about side lengths, is Pythagoras. Pythagoras is going to say in this question, our hypotenuse is 15, and that's constant, it's set in stone. So we can say x squared plus y squared equals 15 squared, right? Our two sides equal our hypotenuse squared. Because 15 is going to be a constant here, why don't we just make this easier for ourselves and just say it's x squared plus y squared equals 15 squared, which is 225. So we might as well just call that 225. Whoop-de-doo. Now, that's all well and good. We could use, normal old Pythagoras here to find, maybe our x value, right? We could, especially if we know y is 3 feet above the floor, we could find x. But maybe that doesn't matter right now. Remember, what we're looking for here is y prime. Now, y prime is going to have to come out of taking the derivative of this. So why don't I just go over here now and say we're going to take the derivative of this function with respect to time. So we'll have to use implicit differentiation on this one. To implicitly differentiate this, we can say the derivative of x squared is 2x. But then, of course, since we're not doing this just with respect to x, we now have to multiply by x prime plus the derivative of y squared, likewise, would be 2y. But again, because we're doing the derivative not with respect to y, but with respect to time, we'll say it's times by y prime equals the derivative of 225. No matter how you slice and dice that, the derivative of 225 just being a constant is 0. Okay, so let's take stock of what we got here. This derivative formula is really nice because it has our y prime that we're looking for. We're trying to get that. We already know what y is, so that's, all well and good. We know what x prime is, that's good as well, but we don't know what x is. But here's the good news. Since we know what y is, we can just use regular old Pythagoras to figure out what x is and then jump back to this formula to solve for our y prime. So why don't we do that? So we don't know what x is when y is 3, so why don't we just say x squared plus 3 squared equals 225. You could subtract 3 squared over And that I guess would give you like 216. I'm not even gonna lie, I didn't write it down on my notes page here. It's whatever, but then you got to square root it. You guys know how to solve Pythagoras at this point. Just minus this, square root it, no big deal. So x equals, I'm gonna round to, let's say 3 decimal places, 14.697. That should be accurate enough. I mean, I could have left it as square root of 216 or whatever, but whatever, who cares? Anyway, now that we know what x is, we know x, we know x prime, we know y, and we're looking for y prime. You might as well just throw that all in right here. So here we go. You know what? I'm actually going to bring this down just so I have a little bit more room. We've got 2 times x, so 2 times 14.697 multiplied by x prime, which is 2.5. And I don't know if I mentioned, just by the way, I think I might have. 2.5 is positive here because x is getting bigger. It's sliding away from the wall. So x is going to become bigger each second. Just thought I maybe should let you know that. But anyway, plus 2 times y. 2 times y is going to be 2 times 3 multiplied by y prime, which is what we're looking for. And that all equals 0. To solve for y prime, of course, I would solve all of this, subtract it over, and then divide by 2 and divide by 3. I'm going to save you all the trouble. I think you hopefully know how to rearrange an equation by Math 31. The answer to this, if you were to solve it to the nearest hundredth, is negative 12.25. And since that's a rate of change of our y and our unit was measured in feet, we can say that's feet for our, our y divided by rate of change. So it's seconds. So negative 12.25 feet per second. Awesome. Now, in case you're wondering why that's a negative number, you should not be too surprised by this. Y is decreasing here, right? As x is getting bigger, y needs to be getting smaller. So the negative 12.25 here indicates that y is getting smaller and smaller and smaller. Now, just intuitively, I could be wrong on this, but just intuitively, just because of how much larger or smaller, depending on perspective, that number is than the 2.5, just intuitively, I would suggest that as a ladder slides away from a building, the rate of change of your y speeds up, whereas the rate of change of your x slows down. I could be totally mistaken on that, but it is what it is. Anyway, here we go. Question B, same original sort of context here, but it says now, at what rate to the nearest hundredth is the angle formed between the ladder and the floor decreasing when the base of the ladder is 10 feet from the wall? Ooh, holy smokes. So it's the same context from before. You can draw another picture if you want. I'll just hold off on it for now. Notice it does say the answer will be in radians. I put that in there just because I don't think we've ever spoken in this course. When you use trigonometry, like sine, cos, tan, etc., in calculus, you have to use radians, because what we're doing is we're comparing an angle measure to an actual linear unit, whether it's a rate of change of your, your height or your width or whatever. You're comparing it to some other linear unit. Degrees, which are a lot more comfortable for measuring angles, they don't really work too well when you're comparing it to anything other than an angle itself. Radians, however, are defined as being based off of the situation that it's in, right? 1 radian is where your arc length matches your radius, for instance, right? It is not an arbitrary unit. It is actually based around the entire situation. So in calculus, whenever you're finding an angle, you always must use radians. We're not using degrees. And if it gave you degrees, you would have to change it to radians, which is kind of a pain. So just kind of a highlight there. You won't really need to worry about this here. Just kind of a disclaimer, make sure your calculator's in radians, and that's what your answer is going to end up getting to here. Anyway, that's a total aside. What I want to do, just to draw a real quick picture again, we know that our hypotenuse is 15. We know this is our x. We know this is our y. We know the rates of change, yada, 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 right? What we're looking for is the rate of change of our angle, the rate of our angle. So our angle between the ladder and the floor, that would be this guy down here. I'll call it theta, right there. We want to find what the rate of change of that is. Now, the question does tell us we're just looking for that rate of change when the base of the ladder is 10 feet from the wall. So that's going to be our x. X is going to be 10 feet from the wall. Now, here's the situation we got. We know that as this ladder is falling, x is going to be getting bigger and bigger, whereas y is going to be getting smaller and smaller. So the rate of change of our x, which is still this 2.5 feet per second, that is still going to come into play here, right? So really, we're focusing in a lot on this x unit here. So when we're trying to compare our angle to the rest of this triangle, just by all this X information it's giving us here, we should kind of be leaning towards more using our X. Now, where I'm going with this is when you're comparing an angle inside of a right triangle, you can use sine, cosine, or tangent. Now, in this case, because all of our clues here are hinting us to use X, I'm going to lean more towards using cosine, because cosine of an angle is the adjacent side divided by the hypotenuse. And the adjacent side in this triangle is your X. So let's set this up. We know a relationship that exists here is therefore cosine theta equals your adjacent side, which is X, divided by your hypotenuse, which is a set in stone 15 always, right? X, I left as X here rather than saying it was 10, because I want an actual relationship that's going to show as this has a rate of change, what's happening with our X and so on, right? We might end up having to use this X equals 10 at some point. We'll just hold off on it for now. So bottom line is, if we're looking for the rate of change of our angle, that means we're looking for theta prime, the rate of change of our angle, we need to take the derivative of this cosine theta. And again, not just with respect to theta, but with respect to time. So the derivative of cosine theta with respect to time is going to be the derivative of cosine theta with respect to theta first. So in other words, it would be negative sine theta multiplied by, this is your chain rule piece, the derivative of theta with respect to time, which is going to be theta prime. Set that equal to the derivative of X with respect to time is not just 1. That's what the derivative of X would be. It's going to be X prime divided by 15, right? Because think of 15 as a coefficient on the X in such a way, right? Anyway, so this is not too bad. We know what X prime is. That was given to us right there. We're looking for theta prime. So that's all well and good. We got that all set clear. But notice it's asking for negative sine theta to type into this formula. Shoot. Well, negative sine theta is going to be, that's going to come out of using some trigonometry here. That's where this 10 feet is going to end up playing in. Let's go back to this triangle over here. I'm actually going to draw a fresh one just so you can see what I mean. 15 is our hypotenuse. We're going to assume at this point the ladder's 10 feet from the wall. And we're looking for sine theta to plug into this equation, this derivative equation, which will hopefully unlock this theta prime. Well, sine theta, I'll write it up here, sine theta is always equal to opposite divided by hypotenuse. The opposite angle, or sorry, the opposite side in this triangle is going to be your y value here. Notice when X is equal to 10, Y is going to have some definite value as well. We can use Pythagoras to solve for it. This is a weird question because usually when I give you like X is 10, you plug it in directly. But in this case, we actually have to use it to find some other piece of information, namely the sine theta. Kind of a bit of a trick, but this is about as hard as they get. I'm not going to fret over this too much. Long story short, if we're trying to get sine theta, opposite over hypotenuse, we need y over 15. Y is going to be some number here. Let's solve for it. 10 squared plus y squared equals 15 squared. If you rearrange this, I can tell you right now, y squared is going to equal, that's 225 minus 100, so it equals 125. Square root that, and y is going to equal about 11.16. So what that means is this is our opposite side, 11.1. Oh, sorry, I said 6. 1/8, my mistake. 11.18 is our opposite side. That is going to go into our sine value here. So if we throw it back into our derivative formula to find our theta prime, we could say negative sine, which instead of saying negative sine, we'll say negative opposite over hypotenuse. So negative 11.18 over 15 multiplied by theta prime equals x prime, which is 2.5 divided by 15. To solve for theta prime, we just need to multiply by 15 on both sides. This is what's kind of a joke here because that just gets rid of that. And then we have to divide by negative 11.18. So theta prime equals 2.5 divided by negative 11.18. And it does say round to the nearest hundredth. So we'll say it's negative 0.22. And technically that is radians per second. It is not measured in degrees. We need to make that very, very clear. It is not a degree. These are radians because radians are the only units that really get used in calculus. If you ever see degrees in this course, change it to radians. For those of you who are unaware how to do that, if you had degrees, I'll say D for degrees. To change it into radians, you just multiply by pi over 180, right? Another way of thinking about it is 1 radian is approximately equal to like 57 or something degrees, right? So if we have 0.22 radians per second, really that means it's going down by like, I'd estimate it close to about 10 degrees per second-ish, somewhere around there, maybe a little bit more. Anyway, that's it for that question. So we got one more question we're going to deal with here. This one I actually like better. I think this one you guys will probably like better too, because it, I don't know, it just works better. I think I said this is the last question. I think there actually is one more. Yeah, there is one more. Sorry, guys. We have a couple more questions. This one goes a little quicker though. Don't worry. So at 1 o'clock p.m., a van is 140 kilometers north of a car. The van is moving west at 60 kilometers an hour, and the car is moving north at 50 kilometers an hour. At what rate is the distance between them changing at 3 p.m. to the nearest tenth? First thing on this one, like one thing that's just weird is having a time, like an actual like hour of the day. That's kind of a silly way of putting this. Clearly 2 hours have passed. So maybe that's going to be a little bit more important. We know 2 hours have passed here. I think drawing a picture is really going to help here. At 1 o'clock, that van is 140 kilometers north of a car. So why don't we say this is the car, and then directly north of that is our van. We'll say that right there. At 1 o'clock is 140 kilometers. Yeah, I'll draw that in there. 140 kilometers. The van is moving west, so the van is moving this way, and the car is moving north. So it's trying to like close this distance in between them. We want to find the rate that the distance between them is changing at 3 o'clock. Well, the distance between them is the hypotenuse here. That's what's going to be changing. Okay, so just to take stock here, one thing that we know right off the bat is there is going to be a right triangle here because west is defined as being perpendicular to north. So we know if we say that this is our x and that this distance is our y, the initial y is 140, of course. How about we say the distance is d? We can say that x squared plus y squared equals d squared. I guess the other thing we can say here is we can take an inventory of the stuff we've got. We know the van is moving west at 60 kilometers an hour. In other words, this x component of our right triangle is going to be increasing at a rate of 60 kilometers per hour. So why don't we say x prime, the rate at which x is increasing, is 60 kilometers per hour. This 50 kilometers an hour is the rate that our y is changing. But what's kind of weird here is because initially they were, 140 kilometers apart, north to south, since y prime, or in other words, the car is moving north at 50 kilometers an hour, that's closing this distance. So it's not going to be a positive changing value here. It's shrinking that distance there. So it's going to actually be negative 50 kilometers per hour. Right? If it was positive 50 kilometers an hour, that would tell you that the cars are getting further apart. That distance would be growing. But this distance right here is actually shrinking by 50 kilometers per hour. What we're looking for in this question is the rate that the distance is changing. So we're looking for d prime. D prime is our big unknown here. The fact that we know 2 hours have passed has actually told us how far they've gone in these x and y directions. Since the van is moving west at 60 kilometers an hour and 2 hours have passed, we can reasonably say that x is 60 kilometers times 2 hours, so 120 kilometers. Again, to make that more clear, the van is moving west at 60 kilometers an hour. 2 hours have passed, so 60 kilometers per hour in 2 hours would be 120 kilometers on this west direction here. As for our up and down direction, north-south, after 2 hours going 50 kilometers an hour, you should have traveled 100 kilometers. So a bit of a trick question here. Y is not 140. Y is actually just going to be 40 kilometers because after 2 hours, that 140 kilometers has shrunk to just 40 kilometers because 100 kilometers have taken off of that. I guess the other thing we can say is obviously with all these, x prime, y prime, d prime, we're going to need the derivative formula. So we'll have to take the derivative of this thing. The derivative of this Pythagoras in this case with respect to time would be 2x x prime plus 2y y prime equals 2d d prime. Since we're looking for d prime, we just have to take stock that we have everything else here. We have x, we found that 120. We have x prime, we have y prime. What we don't have though is the distance d. The good news is if we know our triangle characteristics right here, 120 this way and 40 this way, we can solve for that d value just by using Pythagoras. So we can say 120 squared plus 40 squared equals d squared. Long story short, if you do the math on that, that means d equals 126.49 kilometers. Whew, okay, so all that information all put together. Notice how it was just like a stream of consciousness. You just look at what you got and you try putting it together, draw pictures whenever you can, throw the rest of the information in there. So we just have to throw all these numbers in there. Why don't I'll just jot that all down. I'm just going to do it down here so I have room. 2 times x was 120, times x prime, which was 60, plus 2 times y, which was 40, times y prime, which was negative 50, equals 2 times d, which is 126.49, times d prime, which is what we're looking for. Clearly, you can just add together that whole left side there and then divide by 2 and then divide by 126.14. Long story short, d prime to the nearest tenth is 41.1 kilometers per hour. And I know it's kilometers per hour because remember, d prime means it's a rate of change of our distance. So it's how much our distance is changing by. Since this answer was positive, we can actually say that these vehicles are getting further apart rather than getting closer together, right? And I think the number one thing that's doing that is the fact that the van is moving faster than that car. So the van is trying to, it's building that distance faster than that car would be shrinking the distance, in other words, right? Anyway, so one more question here. Hopefully we're not like totally in like a, confused coma right now or anything, but if you are, remember, just come back, ask me in the Zoom. Last question here. I'm going to give you a bit of a disclaimer on this one. This is not going to be a right triangle question, so we're going to have to use one of those non-right triangle formulas here. Let's get going on this one though. A triangle has two sides of constant length, 15 centimeter and 17 centimeters. The angle between them is increasing at a rate of pi over 24 radians per second. At what rate to the nearest hundredth is the length of the third side increasing when the opposite angle measures pi over 3? Holy smokes, you need to draw a picture on this one. This one is going to be weird. We know a triangle has two sides with constant lengths. So those lengths of those two sides are not going to change. They're just set in stone and the angle's moving apart, right? So if we drew this, how about we say this one is 15, and then let's say we have another one here that's 17. The angle between them is increasing at a rate of pi over 25. So the angle between them, how about we call that theta? We're looking for the rate to the nearest hundredth of the length of the third side. I guess that would be this here to form a triangle. I'll call it x just because I can use whatever letter I want here. At what rate to the nearest hundredth is the length of the third side increasing when the opposite angle, that would be theta here, measures pi over 3? Whew, okay, let's try to take stock of what we've got here. 15 and 17, no point jotting those down, they're already there. We know the angle between them is increasing at a rate of that, so we know theta prime, the rate of change of your angle, is pi over 24. We are interested at the rate that the third side is increasing by, so we're looking for x prime when the opposite angle measures pi over 3, so when theta is just straight up pi over 3. All right, so I guess one of the hardest parts of this question is going to be figuring out what kind of relation we've actually got here. Remember I told you there's sine law and there's cosine law. Sine law only works if you know an opposite pair. If you look in this triangle here, we don't know an opposite pair here. We know 15 and 17, and we know what theta is, but theta is not an opposite pair to either of these angles, right? Opposite to 15 would be this guy up here, opposite to 17 would be this guy over here, and we don't know those, nor do we really care. So that kind of narrows it down. We need to use cosine law because this, I guess another way of saying it, is an SAS triangle, side, angle, side. So cosine law is going to be coming into play here. Cosine law is going to say that x squared, our opposite side all on its own, equals the other two sides squared added together, so 15 squared plus 17 squared, minus 2 times BC, so 2 times 15 and 17, 2 times 15 times 17, multiplied by cosine of your angle, so multiplied by cosine theta. Now, the reason I filled in 15 and 17 here, but I didn't fill in theta, is because theta can change. It is increasing at a rate of pi over 24. These other two sides, though, it did say they're constant, they are set in stone, no ifs, ands, or buts, right? What we're trying to look for here is x prime, which tells us we kind of need to use the derivative of this. If I just took the liberty right now to take the derivative of this, maybe instead, before I do that, maybe we should clean this up a little bit because it's kind of a nightmare. Before I take the derivative, I'm going to say that x squared equals 15 squared plus 17 squared, which is 225 plus something, whatever. Either way you do it, though, it's going to be 514 in total between those two, minus 2 times 15, which is 30, 30 times 17, which is 510, times cosine theta. That is cleaner now. That's going to be easier to take the derivative of. The derivative of that function is going to be 2x x prime, because remember, we're taking it with respect to time, not with respect to x, equals the derivative of 514, nothing at all, gone. So the derivative of now, I guess, negative 510 cos theta is the derivative of cosine theta, which is negative sine. So that's going to force us to become positive 510 sine theta. Ooh, that's a gross theta. Hold on, theta multiplied by theta prime. Okay, believe me, we're almost actually done here. If we take stock of what we've got and what we're looking for x prime. We don't have a darn clue what x is, but guess what? That's what cosine law is for. So we could always come back and use that. So x we'll have to find. Sine theta, well, it's just sine of pi over 3. Just make sure you're in radian mode in your calculator and you've got that one too, no big deal. Multiplied by theta prime, which we actually know is pi over 24. So we got everything except for x. So you know what? Yoink, down here, x prime is going to equal 514 minus 510 times cosine pi over 3. Throw that in your calculator, square root it, and you're going to find that x equals 16.09. That, I guess, is how long this side is when theta is pi over 3. And since that is our side length there, we can just throw it into our derivative formula as well. So going one step further here, we can say it's 2 times x, so 2 times 16.09 multiplied by x prime, which is what we're looking for, equals 510 sine pi over 3 multiplied by theta prime, which is pi over 24. Oh my goodness, this was a long question. Anyway, there I was thinking it was going to be quicker than this. I guess it wasn't. Anyway, so now what we do, evaluate the right-hand side, get a number for that, leave it in your calculator, whatever, divide by 2, and then divide by 16.09. So just rearrange this formula to get x prime all by itself. X prime all by itself is positive 1.80. And I guess since this is a rate of change of a side length, the side lengths here were measured in centimeters, so it's going to be centimeters, and it's a rate of change, so it's per second. Whew, holy smokes. Needless to say, these take a lot of practice. This video has already been like 30 minutes long. Apologize for that, but you know what? They do take some practice. So I guess what that leaves for us is I want you guys to practice on the handout. I know it just says handout. You know, what I mean by that is just, you know, the thing that was in the booklet. The booklet, by the way, if you need a digital copy, it is on Google Classroom. Now it says our unit exam is on Tuesday. That was from before. I just forgot to scratch that out. The unit exam's coming up. Check Google Classroom, stay posted on that. It'll be when it'll be. But when the unit exam does arrive, it's basically just going to be a combination of the last 2 quizzes that we've had from this unit. Or more specifically, it's going to cover all of this right here. The first and second derivative tests. Remember, first derivative test was talking about your intervals of increase or decrease. Second derivative test was talking about your concavity. There'll be some optimization problems. We'll review all this. Don't worry, guys. Vertical, horizontal, and oblique asymptotes. That was for the rational functions. Some very basic curve sketching. Doing this online, it's going to be kind of interesting if we can do even decent curve sketching on this, but we'll see what I put in there. Displacement, velocity, acceleration problems. Those are really useful online. Maybe we'll see a bunch of those. And then, of course, the rates of change of area, volume, and the stuff from today, triangles. Whew. Bottom line is, do what you can do today. We'll space this out. We're not going to rush things by any means. If you need any help, please pop into the Zoom at some time and ask. I can help you with anything on that handout if you wish, and we're good to go. Anyway, best of luck.